In this segment, we take what we have learned about random walks to develop a quantum analog. I'm going to start at the end. Here's the statement of the result that I will explain in this video. We are in the same scenario as the last video. There's a graph that is known to us, but each vertex of the graph has some data that we don't initially know, and which has an associated cost for us to learn it. I will define the parameters S, U, and C here more formally later, but think of them in analogy to the randomized case. S is the cost of setting up the initial state of the quantum walk. U is the cost to perform one step of the walk, and C is the cost to check if an item, a vertex, is marked. Again, all these costs are incurred by having to learn the data at a given vertex. Now suppose that the graph has spectral gap delta and that an epsilon fraction of the vertices of the graph are marked. The theorem says that there is a quantum algorithm to find a marked vertex with constant probability with total cost S plus 1 divided by square root of epsilon times the quantity 1 divided by square root of delta times U plus C. So you see that compared to the classical case, we have replaced 1 over epsilon with 1 over square root of epsilon, and 1 over delta with 1 over square root of delta. So we have square root speedups with respect to both of these factors. This might remind you of Grover's algorithm, where we also saw a square root speedup. And indeed, there are many analogies with the quantum walk that we're going to design and Grover's algorithm. Let's look at an application of this theorem to the element distinctness problem, as we did in the classical randomized case. I will hold off on the formal definition of S, U, and C in the quantum case for the moment, but in this application they have exactly the same values as in the classical case. When we do a walk on the Johnson graph on subsets of size R, then S is R, U is 1, and C is 0. We again have epsilon being r squared divided by n squared, and delta being 1 divided by r. So the formula gives r plus square root of r times n divided by r. However, now, unlike the classical case, we can get something non-trivial. By taking r equal to n to the 2/3, then the entire bound becomes n to the 2/3. So this gives a bounded error quantum query algorithm for the element distinctness problem that makes order into the 2/3 many queries. And this is known to be tight. This upper bound was first shown in a remarkable paper by Andres Sambinas, one of the pioneers of the application of quantum walks to quantum algorithms. Now let me say something about how to prove the theorem from the first slide. At heart, it can be viewed as an extension of Grover's algorithm. There are going to be 3 states that are important for the algorithm. The good state, which for the moment you can think of as being analogous to the superposition over all of the marked vertices. The bad state, which will again be analogous to a superposition over all unmarked vertices, and a uniform state, which will be analogous to a uniform superposition over all vertices. By assumption, we know that the good state has overlap epsilon with the uniform state. So by doing order 1 over square root of epsilon many rounds of the Grover iterate, we can arrive at a state that has constant overlap with the good state. When we measure this good state, we will have constant probability of seeing a marked vertex. By the phase kickback trick, reflecting about the bad state can be implemented with one call to an oracle which determines if a vertex is marked or not. The complexity of determining if a vertex is marked is C, the checking cost. We now totally understand the appearance of the term C divided by square root of epsilon in the complexity. The more interesting and new part of the algorithm is reflecting about the uniform state. This is where the quantum walk comes in. We will see that reflecting about the uniform state can be done with order 1 over square root of delta many steps of the quantum walk. Letting u, the update cost, be the cost of 1 step of the quantum walk, then the cost of this reflection will be u divided by square root of delta. Now we can understand the formula for the cost of the algorithm by analogy with Grover's algorithm. S is the cost to set up the uniform state, and we do 1 over square root of epsilon many applications of the Grover iterate. In the Grover iterate, we reflect about the uniform state. The cost of this is u divided by square root of delta. And then we do a reflection about the bad state, and the cost of this is c. So this is the high-level idea. I still need to tell you how we actually implement a quantum walk, and where this u divided by square root of delta term comes from to reflect about the uniform state. Let's start thinking about how we can define a quantum analog of a random walk on a d-regular graph. The first thought might be to just have one register which holds the name of a vertex. Then our walk operator would send the state labeled by vertex j to a uniform superposition of its neighbors. This definition has a problem though. What's wrong with this? Well, this won't be a unitary operation. Two different vertices can have the exact same neighborhood. Thus, this operation is not reversible. This leads us to think that we need to add some notion of history to remember the vertex that we are coming from. We will instead think about doing the walk on the edges of the graph rather than the vertices. Our states will have two registers, each labeled by a vertex. Being in state j tensor k means that we are currently in vertex j and came from vertex k. Using this definition, let us see what the good and uniform states of our walk should be in analogy with Grover's algorithm. Let M be the set of marked states. Recall that we assume that the cardinality of M divided by n is epsilon, and I will further assume that epsilon is less than a half, since if epsilon is larger than that, we can easily find a marked vertex with a randomized algorithm. For vertex j, let ket in j be the uniform superposition over all the neighbors of j. The good state, psi good, is the uniform superposition of the states j tensor nj over all marked vertices j. The bad state is the analogous superposition over all unmarked vertices. The uniform state, the state in which we start our quantum walk, is the uniform superposition over all j of j tensor nj. So now we've formally defined the states we need, the good state, the bad state, and the uniform state. Just as in the standard Grover setting, the algorithm will take place in a 2D plane spanned by the good and bad states. The uniform state is sine theta times the good state plus cosine theta times the bad state, where theta is the arcsine of square root of epsilon. So now we can emulate Grover's algorithm. We start in our analog of the uniform state, the state u, and for the floor of pi divided by 4 theta iterations, we do the operations of reflecting about psi bad and reflecting about the uniform state. Then we measure the first register to see if it is marked. Okay, I will quickly go through this slide as the analysis is exactly the same as in Grover's algorithm. You can show that with the choice of the floor of pi divided by 4 theta many iterations, this algorithm will succeed with probability at least 1 minus epsilon. As I mentioned before, to reflect about psi bad, by the phase kickback trick, it suffices to check if a vertex is marked or not. And by definition, the cost of checking if a vertex is marked is exactly c. What I still need to tell you is how to implement the reflection about the uniform state. This is the interesting step where the quantum walk will be used. Remember that our interpretation of being in the state j tensor k is that we are currently at vertex j and came from vertex K. Let's think about how we could do a step of a classical random walk using this syntax. We could first put a random neighbor of the vertex in the first register into the second register, and then we could swap the two registers. It turns out that to develop a quantum analog, it is easier to combine two steps of the walk together. So we first put a random neighbor of the vertex in the first register into the second register, and then we put a random neighbor of the vertex in the second register into the first register. So this is now the notion of a classical random walk that we want to quantize. Here's how we can develop a quantum analog. Recall that the state Nj is the uniform superposition over the neighbors of vertex J. The quantum walk operator is a product of two unitaries, W1 and W2, emulating the two-step classical process we described on the last slide. When the first register is in the state J, W1 applies a reflection about Nj to the second register. This is again analogous to what we do in Grover's algorithm. We are reflecting about a uniform superposition over all neighbors of vertex J. Likewise, when the second register is in the state J, W2 applies a reflection about Nj to the first register. One step of the quantum walk is then the product, W2 times W1. It's not immediately clear why this is a good definition for a quantum walk. Let's see why it works. Let Z be the subspace spanned by the vectors of the form J tensor Nj and vectors of the form Nj tensor J. We can relate the eigenvalues and eigenvectors of the walk operator W in Z to the spectrum of the normalized adjacency matrix of G. The first thing to note is that the uniform state U is fixed by both W1 and W2. Thus U is an eigenvector of W with eigenvalue 1. Also, of course, U is in the subspace Z. It turns out that if G is connected and not bipartite, then U is the only eigenvector with eigenvalue 1 in the subspace Z. Now let lambda 1 through lambda L be the eigenvalues of A whose magnitude is strictly between 0 and 1. Then the eigenvalues of W with non-zero imaginary part and that correspond to eigenvectors in Z are exactly e to the plus or minus 2I theta j, where cosine theta j is equal to the magnitude of lambda j. All remaining eigenvalues of W corresponding to eigenvectors of W and Z have value minus 1. The high-level takeaway is that we have a very direct correspondence between the eigenvalues of A and those of the unitary W. So here's an illustration of the eigenvalues of W. The key fact that we need is the following. We know that U is an eigenvector with eigenvalue 1. If the graph has a large spectral gap delta, then all other eigenvalues will be bounded away from 1. In other words, they will be of the form e to the 2I theta, where theta is at least the square root of 2 delta in magnitude. This allows us to implement the reflection about the uniform state with a cost that is proportional to 1 over square root of delta. The idea is to use phase estimation. Given an eigenvector v of W, we want to multiply its phase by minus 1 if and only if it is the uniform state U. Otherwise, we want to leave it alone. So we estimate the phase of the eigenvalue of V up to a precision a bit smaller than square root of delta. If our estimate tells us the phase could be 0, then we multiply the phase of V by minus 1. Otherwise, we leave it alone. Doing phase estimation up to precision square root of delta divided by 2 can be done with order 1 over square root of delta applications of W. We define the update cost to be the cost of performing W. So let's now see how we can implement W. To implement W, it suffices to implement W1 and W2. Let's focus on implementing W1. The case of W2 is similar. To implement W1, it actually suffices to be able to do the map that sends the state J tensor 0 to J tensor in J, and also to be able to do the inverse of this operation. If we can do this, then to implement W1, we can simply apply the inverse of this map, multiply the phase by -1 if the second register is not 0, and then apply the map again. So this is a useful formulation to help compute the update cost. In particular, from this we can see that the update cost in the case of the walk on the Johnson graph is just 1. We have seen there are many ways in which a quantum walk is modeled on Grover's algorithm. Can we use a quantum walk to rederive Grover's result? Definitely. I saved this as a puzzle for you. The main thing to think about is what graph should you do the walk on in order to rederive Grover's result. Finally, let me finish off with one more application of a quantum walk. This is to the problem of determining if a graph has a triangle. When you have query access to the graph so that you can ask questions of the form, is there an edge between vertex I and vertex J? An early application of quantum walks gave a quantum algorithm for this problem, making n to the power 13 over 10 queries. On the other hand, we know that the randomized query complexity is theta of n squared. The current best quantum algorithm for the triangle finding problem makes n to the power 5 over 4 many queries. And we don't have any lower bound larger than omega of n. This problem remains a great open problem and a great test for quantum algorithm designers.